Right, everyone, we're on to the last type of asymptote that we're going to look at, and that's an oblique asymptote. By far my favorite asymptote, as these really are quite fun. So oblique just means at an angle. So an oblique asymptote is very similar to a horizontal asymptote, except it's one that occurs at an angle. So it's something like the graph will tend towards that line as x tends to infinity, except it's not a horizontal line, it's a diagonal line. And it happens in exactly the same way as a horizontal asymptote happens. The limit as x tends to infinity of a function, instead of the function tending towards a horizontal line, it now tends towards an oblique line. So remember we knew that a horizontal asymptote existed if the degree on the bottom was equal to or bigger than the degree on the top. Now an oblique asymptote will occur if f of x equals g of x over h of x, so basically two expressions over each other. There will be an oblique asymptote if the degree on the top, so the degree of g of x, equals the degree of h of x, so the degree on the bottom, but plus 1. So basically the degree on the top must be 1 more. And the idea is that the limit as x tends to infinity of f of x lands up being an oblique line, an mx plus c. I called it ax plus b, but it doesn't matter. It lands up being a line at an angle, not a horizontal. So we're going to go through a little bit more slowly through these ones because they're new to us. We haven't done obliques before, and they definitely take a little bit more getting used to. So let's look at a couple of examples. Determine the oblique asymptote of f of x equals x cubed over x squared plus 1. So first of all, how do I know an oblique occurs here? Because x cubed has a degree 1 more than x squared. So that has a degree 1 more than x squared at the bottom. So that's how you're going to be able to identify. You can't have a horizontal asymptote and an oblique asymptote. It's one or the other because the conditions under which the one exists is completely different to the other. They are mutually exclusive. So let's have a look. What do we do here? Well, basically we need to rewrite x cubed over x squared plus 1. I want to rewrite it. Now let me show you how I'm going to do this. What I'm going to do is I'm going to say, right, what is x cubed equal to? X squared plus 1 multiplied by something. So remember, if I said to you, what is 6 divided by 3? You would say, so if I said to you, what is 6 divided by 3? You would say, well, 6 equals 2 times 3. So 6 divided by 3 is 2 because 2 times 3 is 6. So I'm doing exactly the same thing. I'm saying to myself, what is x cubed divided by x squared plus 1? Well, can I rewrite x cubed as x squared plus 1 times something? Now, a couple of difficult things here in that I could do long division, but that's a nightmare, and so I'm going to avoid that. And so we're going to do this by something called inspection. It's really quite nifty. Our problem, though, is that no one said that x squared plus 1 actually goes into x cubed. So there could be a remainder. In fact, there's always a remainder. So let's have a look. So what I say to myself is, what would I have to multiply x squared by to get x cubed? And you'd have to multiply by x. Now, once I've done that, let me just check what this is so far. So let us check. If I multiply it out so far, I get x cubed plus x. Now, how do you know when to stop? Because x cubed plus x isn't right. This is not that. Now, why is it not that? It's not that because x squared plus 1 does not go exactly into x cubed. Now, how do you know when to stop? Now must I fix that x? You always stop when you're accurate to an exponent 1 less than the x cubed. So it's quite difficult to explain. So you stop when this expression is accurate to a degree. That doesn't say degree, so let me just say that again. to a degree 1 less than the numerator. So in this particular example, this numerator was x cubed, so the numerator is x cubed. So we're going to stop when we're accurate at x squared. So let's have a look at this. Are we accurate at the x squared level? I so far know that I have x cubed plus x when I multiply that out. I'm not meant to have x squared, so there are no x squareds here, and this is correct. And so because this is correct, yay, I can stop worrying. So once I'm accurate to a degree 1 less than that numerator, then my bracket is complete. So therefore, my bracket is complete. Okay, now here's the problem. This isn't right. That plus x is not meant to be there. So because this isn't right, I now need to correct it. So how I correct it is I say, well, if this bracket at the moment, those multiplies out to x cubed plus x, and I need it to equal x cubed, I'm now going to correct it by subtracting x. Because now, if I work out that entire right-hand side, I get x cubed plus x minus x, in which case it's x cubed. So this is now a true statement. Now, this was kind of confusing, so I promise you as we go over quite numerous examples, we'll start to be a little bit happier with this. So let me just rewrite this a little bit more neatly. What I'm arguing is I'm arguing that x cubed equals x squared plus 1 times by x minus x. Now let's just check that this is actually true. If I multiply this out, I know I get x cubed plus x minus x, which, what do you know, equals x cubed. So this is true. Now why is this important to me? How does this help me? Well, what was the graph? The graph was x cubed divided by x squared plus 1. So because this is an expression, this line over here, it's an equation. If you divide the left-hand side by x squared plus 1 to represent the graph, you must divide everything by x squared plus 1. So I'm going to divide that term by x squared plus 1, and I'm going to divide this term by x squared plus 1. So actually, if I rewrite this graph is equal to x minus x over x squared plus 1, which is pretty nifty. Now, why is this important? Why would you rewrite this graph as this expression? Now, basically what I'm saying is this is very much the same as if I said to you, what is 6 divided by 4? You would say 6 divided by 4 is 1 remainder 2. I don't know if you remember remainder from primary school, but you would say 4 goes into 6 once, and then there was a remainder of 2. So this is exactly the same thing. This is the number of times that x squared plus 1 goes into x cubed, and this is almost my remainder, if you think about it that way. So again, how does this help me? What I want to do is I want to know what is the limit as x tends to infinity of f of x, because that's what an oblique asymptote and a horizontal asymptote are. They're as x tends to infinity, what does the graph tend towards? Now, this equals the limit as x tends to infinity of x cubed over x squared plus 1. Now, we did this in the previous video on horizontal asymptotes. If you divided the top and the bottom by x cubed here, you simply get undefined, and so then this limit doesn't exist. But that's just because we haven't used a clever method to go about doing this. Can we rewrite this x cubed over x squared plus 1 as x minus x over x squared plus 1? Now, if you have a look at this, the limit as x tends to infinity of this remainder part will be x divided by, so it'll be infinity divided by infinity squared. This tends to 0. Now, how do I know that? Well, when I did the horizontal asymptotes, we discussed the fact that if the bottom has a degree bigger than the top, it always just tends to 0, because basically it becomes divided by an absolutely massive number. So even though you have an x on the bottom is infinity squared. That's huge. So that tends to 0. And what does the graph tend towards? The graph will tend towards x. So the graph will tend towards y equals x. So basically what lands up happening here is whatever you land up with here, that lands up being my oblique asymptote. So you don't have to show all this working at all. I shouldn't say horizontal asymptote, I should say oblique. I was doing all this working to explain to you why we were even doing this. In future, I can just identify that whatever's in that bracket is my oblique asymptote. And this is why. The y is at the bottom here. I think it's really important that you understand why. The y is the fact that if you rewrote this function as these two parts, the second part tends to 0, which means as x tends to infinity, your graph is going to tend towards x. So it's going to tend towards y equals x. So it'll tend towards the line of y equals x, which basically means it's going to tend to infinity. But as x tends to infinity, it'll tend towards the line y equals x, which is pretty cool. Now there's something else really, really, really important here. A vertical asymptote is where x is not allowed to be something. But there's no reason why you can't cut through an asymptote if it's an oblique asymptote. Because an oblique asymptote isn't a value that's not allowed to happen. It's a value or a line that the graph tends towards at the extremities. So as x tends to infinity or negative infinity. No one said that the graph can't go straight through that asymptote. So how do you know? Very, very useful to know. How do you know if this graph is going to go straight through that asymptote? Okay, now this is pretty nifty. If this graph was going to go straight through the asymptote, it would be where the graphs of y equals x and this graph equals each other. So I'm just going to fill it in here. That's graph of f, and that's y equals x. This would be where the graph of f of x equals the asymptote, because that over there is the asymptote. So there's nothing wrong with a graph going straight through an oblique asymptote, because it's not a value that x is not allowed to be. And that's the problem in normal maths. We often say to you, normal maths, an asymptote is the line that a graph tends towards but never touches. Now that's not true. It is a line that the graph tends towards at the extremities. It's fair game, in the middle of the function. There's no reason why the function can't go straight through an oblique or horizontal asymptote. So let's go back to this point over here. This is where f of x would equal your asymptote. Now, how would these ever two equal each other? These two would only ever equal to each other if this was 0. So if this remainder is 0, it's the point where these two hit each other exactly, where x cubed divided by x squared plus 1 is exactly x. That's where they'll meet each other. So this minus x over x squared plus 1, that has to be 0. Now the question is, can x over x squared plus 1 ever equal 0? And the answer is yes. Well, my denominator can't be 0 because then it'll be undefined. But when x is equal to 0, that remainder of x over x squared plus 1, that term will be 0. In which case, these two graphs will hit each other. So in this particular example, y is equal to x is the oblique asymptote, and the graph will cut the oblique asymptote at x is equal to 0. Now, if a graph ever cuts an asymptote, that's considered a really important point, and you would have to label it on the graph. So, and the graph will cut the oblique asymptote at x is equal to 0. And if I go, just out of interest, if I go put 0 into my function, I would get 0 cubed, which is 0, divided by 0 squared plus 1. So you'd get 0 over 0 plus 1, which is 0 divided by 1, which is 0. So actually, it would be the point 0, 0. This graph will go straight through that oblique asymptote. It's pretty nifty. Now, it's fairly rare that, I suppose it's not fairly rare. It sometimes happens that this happens, but often the graph doesn't go anywhere near the oblique asymptote until the extremities, and then it doesn't hit it. So we're going to look at the next couple of examples, and we're going to say to ourselves every time, should I expect this graph to hit the asymptote at some point or not? Now, this is a bit of information overload. It just took us 15 minutes to look at one oblique asymptote. It does get faster, but I do want to make sure that we understand fully. So let's look at example 2. Determine the oblique asymptote of g. Now notice the degree at the top, we've got an x squared, the degree at the bottom is x. So the degree at the top is 1 more than the bottom, hence oblique. Okay, so what I'm going to do is I'm going to say, right, 2x squared plus 7x minus 4 has to equal x plus 1 times by something. There's probably going to be a remainder, but I'll worry about that later. So I said to myself, what does x have to multiply by to get 2x squared? Well, this would be 2x. Then personally, I pause and I multiply this out so far. So far, I've got 2x squared plus 2x. Now remember, this needs to be accurate to a degree 1 less than the numerator. Did I say denominator up here? I said numerator, good. I was thinking correctly. So this needs to be accurate to a degree 1 less than this guy. So this needs to be accurate to the x term. So if the x term isn't accurate, I still need to add into the bracket. Now, this isn't accurate. I actually need 2x squared plus 7x. And so this is not yet accurate to the x term. So I need an extra 5 x's in order for this to work. So what happens here is I now know that I need to add a constant in here. Obviously I can't add more x's because then I could have just added more x's into this first term. So I'm going to add, if I think about it, if this is a plus 5, I would now get plus 5x, and I'd get plus 5. So now this would add to 2x squared plus 7x, because remember, as long as those two are happy, I'm fine, plus 5. Now that's not a problem. You need to be accurate to 1 less than the x squared, so the x term, and then you don't have to worry. You can use the remainder to fix the problem. Now plus 5 isn't right. Plus 5 needs to be minus 4, because that's not what I had. I didn't have plus 5, I had minus 4. So how do I go from 5 down to minus 4? I'm going to subtract 9. So basically, if you multiplied those two brackets out now, you would get 2x squared plus 7x plus 5, and then you'd get minus 9, which would land you up at minus 4. So I've basically rewritten this numerator in this weird way. Why have I done that? Well, the shortcut method, the shortcut answer is, there's your oblique asymptote. I don't have to explain anymore. I am going to explain in a moment. My oblique asymptote is y equals 2x plus 5. I don't have to explain any more than that. Will this graph cut the oblique asymptote? So if I asked myself, will the graph cut the oblique asymptote? Oh, that does not look like cut, so let me write just a little bit neater. Cut this asymptote. Now the answer here is no. Why? Because the remainder is 9. Well, it's actually minus 9. Now, can that remainder ever be 0? No. So this cannot be 0. And if that cannot be equal to 0, it means that your graphs will never hit each other. Remember, if you want the graphs to hit each other, you need a 0 remainder. And this remainder is -9, and that remainder can never be 0. Which means, just per chance, when we graph this in our graph section, this graph will never go through the oblique asymptote, but it will tend towards the line y equals 2x plus 5 as x tends to infinity. Now, I could explain this, and I probably should, just because it's our second one. Let me just quickly explain this. If you take 2x squared plus 7x minus 4, and you divide by x plus 1, so basically I divided, let me change color so I can see it a little bit more easily. Basically I divided this side by x plus 1, so I must divide this plus x plus 1, divide by x plus 1, so I get 2x plus 5, and then I must divide this by x plus 1. Now basically the idea is, if you take the limit as x tends to infinity of this, it's the same as taking the limit as x tends to infinity of that. And as x tends to infinity, you're going to get 9 over an absolutely massive term. So this will tend to 0, and the graph will tend to that. So that's why that's my oblique asymptote. This is also a nice way to see why the graph won't ever cut this asymptote, because if you're trying to say to yourself, can this graph ever equal that line? Well, the answer is it would only be equal if this that remainder could disappear. Because if that disappeared, then those two graphs could be equal to each other. But the problem is -9 over x plus 1 can never disappear, because x plus 1 can't be 0, that's the denominator, and 9 will never be 0. Great, let's try another one. Hopefully these get a bit easier. They are quite heavy to start with. So example 3. Determine the oblique asymptote of f of x equals x plus 4 over x squared plus 4 over x plus 2. I know it has an oblique asymptote because the degree on the top is 1 more on the bottom. So is 1 more than the bottom, I should say. So how can I rewrite x squared plus 4? Well, I'm going to rewrite it as x plus 2. Now, let me just make a note to myself. I don't know why I wrote x to the power of 4. That was daft. Let's change that. That should be x squared. Now, what I've noted there is that's x squared. So I know that I'm done in my bracket when I'm accurate to a degree 1 less than that. So I need to be accurate to the x term. So the x term, which means no x's in this case, has to be accurate, because I see no x's in that left-hand side. So x times by what will give me x squared? X. So if I multiply this out so far, am I accurate? So far I've got x squared plus 2x. Now that plus 2x is not accurate. I should not have that. I need no x's, and I mustn't move out of the bracket until I'm accurate to the x term. So that means I'm going to have to subtract 2x. This is what I need to happen within this bracket. So how does that happen within the bracket? Well, I would need to say minus 2, so that I could say, right, I now have minus 2x. When I do that, minus 2x and minus 4. So now I actually would have, if I change color, so far I would now have x squared plus no x's, which is exactly what I wanted, minus 4. So am I accurate to the xth term? Yes, I am. X squared is what you want, and no x is perfect. But I don't want minus 4. I need this to be plus 4. So how do I get from minus 4 to plus 4? I'm going to add 8. So now I've rewritten my numerator. This allows me to see my oblique asymptote. So my oblique asymptote is at y equals x minus 2. And will the graph cut the asymptote? The remainder is 8. So the question is, can the remainder be 0? No, it can't be. So I'm going to say, but the graph will not cut the asymptote. The graph will not cut the asymptote because the remainder can never equal 0. So that's because the remainder is 8, and 8 can never equal 0. So hopefully you're picking up the fact that the remainder has to have an x in it if it's going to be able to be equal to 0, because a constant can never be equal to 0. So as long as your remainder is a constant, your graph never cuts the asymptote. Once the remainder has any sort of x in it, then you're lucky. Then the graph will cut the asymptote. Okay, I'm hoping this is feeling a little bit more comfortable. So last one. Determine the oblique asymptote of h. You'll notice there's an x cubed and there's an x squared. So it's one more, so it's perfect for an oblique asymptote. So can I rewrite x cubed plus 5x squared plus 6x minus 10 as x squared plus 2x minus 8 multiplied by something? Now let's just quickly check how accurate do I need to be. If this is x cubed, I need to be accurate to the x squared term before I move out of the bracket. So what must I multiply x squared by to get x cubed? This needs to be x. So I multiply this out so far. So now I've got x cubed plus 2x squared minus 8x. So this is correct so far. This is not correct. No, that's not good. This needs to be at positive 5x squared. So that means I'm missing a plus 3x squared. Remember, none of the other terms matter because you can fix them in the denominator if you like. So I need a plus 3x squared, which means I think this needs to be plus 3. Why? Because if I just change color, that'll give me plus 3x squared, which is what I need, and then plus 6x, don't really care about the x's, and minus 24, also don't care about them. So now what have I got so far? Because now I need to figure out what my remainder needs to be to fix the problems. So far I've got x cubed plus 5x squared, accurate, which is perfect. Anything else which is inaccurate I can fix. So minus 8x plus 6x is minus 2x and minus 24. Now what do I need this minus 2x to be? I need that to be at plus 6x, which means I need to add 8x to fix the problem, because if I add 8x I will get to 6x. And lastly, I need to be at negative 10 on my constant, and I'm at negative 24, so I need to add 14, I think, to get to negative 10. So I'm going to add 14. So how does this help me? Well, this is great. There's my oblique asymptote. My oblique asymptote is at y equals x plus 3. And I will indeed cut the graph. The graph will cut this asymptote because have a look at my remainder. My remainder is 8x plus 14. Will that remainder ever equal 0? Absolutely it will equal 0. So the graph will cut the asymptote. So the graph will cut the asymptote, and when the remainder is 0. So when 8x plus 14 equals 0, so 8x would have to equal to minus 14. If you divide it by 8, I get minus 14 over 8, which I'm pretty sure can simplify to minus 7 over 4. So at minus 7 over 4, I'm not going to bother going to put that into my graph to figure out the y value. I would do that if I was plotting, because we always plot a point where the graph cuts the asymptote. But absolutely, I can work out that point. So this graph will cut the asymptote simply because the remainder did have the potential to be 0. Great. That was quite a mammoth task. I really love oblique asymptotes. I think they really are fun. But it might take quite a bit of time to get used to. We are going to do a mixed asymptotes video, and therefore hopefully you'll be able to see all of them in practice, and then we'll practice them again when we start actually drawing these graphs. So eventually oblique asymptotes become second nature to you. Okay, cool. That was fun. Well done.